Welcome to PDH Hour with Glen. I'm your host, Glen Toepfer, and today I want to share with you the shocking truth behind failing compaction tests. Is it really your gauge, or are there other hidden errors that may be sabotaging your project? And before we get started, I want to give you a brief reminder here. Previous webinars can be found on the CQA Solutions website. You can click this QR code. As a reminder, though, unfortunately, only people that attend the live version can get the PDH credit hours because we can't confirm how long you actually watched it otherwise. So an outline of what I'm going to go over today. First thing is going to be just a brief introduction, just briefly discuss the purpose of compacted clay soils, or compacted soils really. Doesn't have to be clay. Why I chose this topic. We'll look at some projects that kind of explain that. Nuclear gauges. We'll look at how they work, the importance of calibration and standardization, how these provide the baseline for your test results. And then I'll get into the math behind the results to give you a little better understanding for those of you that haven't been doing it for a long time. Nuclear gauge test results, other variables that impact the gauge that don't necessarily impact other test methods like the sand cone, then compaction test results. We'll look at all the other variables that are pretty common to any method you choose. I just broke it up into gauge specific and not gauge specific. Moisture density testing, the result interpretation as well, taking the test, things that impact the test, and then interpreting the result, which you'd think would be fairly straightforward, but that's not always the case, hence the reason for the webinar. Nuclear gauge confirmation and verification methods. Then I'll briefly give you an overview, introduction to the next webinar, and we'll get into questions and answers. And regarding the questions and answers, please use the Q&A function on your browser, and I will try and address those at the end. We should have a few minutes at the end of the presentation today, and I'll address your questions then. All right, well, let's get started on the main topic here. What is the purpose of compacted clay soils or compacted soils? I keep calling them clay, but they don't have to be clay. I'm just used to dealing with primarily clay liners, but typically they're going to serve as a foundation, and that provides increased load-bearing capacity, such as structures for roadways, reduced settlement, which improves stability and shear strength. The compacted clay liners, low permeability soils, and most of those you want it fairly homogeneous to alleviate vertical pathways such as sand seams or anything that could bring water or other things up into your compacted soil and cause it to fail over time. So as I mentioned, I want to look at, I think, it's 4 projects that over the course of my career and thinking back through this made me realize there's a real need to discuss this topic. First project will start back in 1993, about 3 years after I started in the industry. On this project, nuclear density testing, the first lift continued to fail. Low density values, we couldn't get it to pass the compaction value. As a background, the material was obtained from an on-site stockpile. It was sampled 5 months prior to the construction. All the soils were pre-qualified. It's noteworthy, I did the sampling. It was sampled by the same technician, and I was doing the compaction testing. And the contractor compaction, it appeared visually adequate. The machine was walking out of the lift, pounding the pin in for the direct transmission measurement. The pin was hard to pound in, so it seems like it should pass, but we weren't meeting the 90%, 92%, whatever that project was. We were falling well below it. So I ended up consulting my notes and looking back at my sampling notes, which is a reason, I think that the technicians that are going to be on the job, it's important that they sample because they get a feel for what's there. And I looked back for the notes and it still didn't make any sense. So I started looking back at survey notes, and I thought, well, let's check the elevation. So I used a hand um, level with a hand rule, and started checking the elevation. And sure enough, I figured out that the top part of the stockpile, basically everything we had sampled, was gone. And the surveyors were out there a day later and they confirmed that. But this was back before the days of GPS. GPS wasn't on all the site. Surveyors weren't on site, they were on call, typically required a day or two notice to get out there. So all that material that we pre-qualified was gone. So it didn't matter what we were doing with the gauge, it just wasn't going to pass. And part of the reason that led me to start looking at it is the material should have had a wet density of around 140 pounds per cubic feet, but our tests were coming out with 128. And I started looking at the different proctors and realized they didn't correlate. So that led me to looking at the elevations. Resampling was required. And in part, this happened, the owner used it all as daily cover, and they didn't think there was going to be that much variability in the soils. So hence, they didn't say anything about it. So moving forward to 2002, I was on a job site nearby, working near another technician about maybe 10 miles away. And my job got rained out, and I called him, see if he wanted to go out to lunch or something. And he said, sure, but he wanted me to stop by and look at his project. He was having problems with a density test passing over there. And I get over there, it's a downpour, and he's actually running the compactor 563, but he shouldn't have been, but that's a whole nother story. The contractor was so busy trying to add water that he was trying to help him out. But yeah, it's a downpour, and they actually had the water trucks running trying to add water. The material's looking like soup, and they can't get it to pass moisture. And the compactor was sinking in. It looked like slop. And also noteworthy, I guess, is that the technician was using a hand tamper to get a void-free surface. And he showed me what he was doing to test, but in that slop, you had to do something just to smooth it off, or it just about would flow away. And you can check out more of this. I did a blog on this years ago on my Uncontained if you want to look at it deeper, but I'm just giving you some highlights here as an example. Excuse me. But there's some questions really. What caused the issue? It's going to be the common question for all these projects here that we look at. Why didn't the engineer stop this? Why didn't the earthwork contractor stop this? And why didn't the owner stop this? I think these are important questions when you're dealing with soils related issues such as this. A lot of your contractors are experienced with earthwork, and they should recognize there's a problem. If they got a problem, they should stop and get it figured out, not keep going. And I mean, they were spending, I don't know, a fortune on adding water. Luckily, there was a river nearby, but they still had the transportation costs. So what caused the issue? The firm we were working for tried to cut costs on annual calibration, so they purchased a do-it-yourself nuclear gauge calibration system. They had a junior engineer calibrate the gauges. She had no training or previous experience. She just had to use a manual. And the results ended up speaking for themselves. Everybody's projects were screwed up. And then, another thing that complicated the issue was the field technician had a lack of experience. He should have known better. He should have known that the material, there's something wrong with the material if you got to add that much water to it. But he had total reliance on the nuclear gauge because he was new to the testing. And so it's a shame in that regard. Why didn't the engineer stop it? They were getting the paperwork on a daily basis. Our paperwork was required to be turned in. There was total reliance on the technician. The engineer was unaware of other confirmation methods such as the sand cone, and they didn't know what to do. They didn't want to ask others. And how I had figured it out on my own job site was that I was having problems with my gauge, and I ended up doing sand cones and moisture tests and figured out the gauge was wrong, but it wasn't consistently wrong. There would always be, you couldn't put in any type of offset that would get it from one day to another to pass a test, really from one test to another. And then we found out that they had calibrated the gauges internally. So The other questions, why didn't the earthwork contractor stop this? That's a good question to me. They should have. They were a well-known earthwork contractor. They did work on roadways, other low permeability soils. They should have stopped it, but I think it might have boiled down to change orders. The client had really deep pockets, so maybe they just wanted to get paid to keep moving stuff. I don't know whatever happened there. I just know it was an issue and I wasn't involved on that side, but it's something that people need to ask because most of these contractors are experienced. Why didn't the owner stop it? That's another big thing. They weren't involved in the project on a daily basis or even a weekly basis. And then they had total reliance on the CQA and the contractor that they were doing things right. So that can sometimes burn you. Third project, move ahead to 2016. This was one where we had 3 acres. Final lift was placed, and we were using the best fit line of optimum curve, and the test continued to fail. No matter what you did, they'd always fall below the best fit line of optimum acceptability. Test had to be above the line to pass, below the zero air voids curve, which isn't shown here, to pass. And no matter what you did, they'd fail. And I did microwave samples on them. I did drive cylinders on them, confirmed that the gauge was correct. It didn't need any corrections. There was something wrong. And the test, even if they correlated back to the proctor and the borrow source area, was wrong. They wouldn't pass. So again, what caused the issue? Why didn't the engineer stop it? Why didn't the earthwork contractor stop? The issue itself, I thought, was a high silt content, and I still stick by that today. We never really did find out because we got a couple tests to pass, and the rest of them, the contractor ended up removing and putting more material on. But both the engineer and contractor were reluctant to take appropriate steps at the time to solve the problem. Why didn't the engineer stop it? I suggested resampling. They didn't want to do that because there was regulatory approval involved for all the samples. So they didn't want to have that delay. They didn't want to go through the process and have to explain why they needed more soils when they were all approved. Earthwork contractor, really theirs was just no sense of urgency. It was a final lift. They could play with it. They were still working on the other half of the cell. So, everybody'd be done at 5 o'clock and I'm there till 6 or 7 because they're reworking it yet again and trying to compact it. But ultimately we ended up removing a portion of it when it did become a point where it would tie them up, and they got it passed with different material. So jump ahead now to 2022. We were doing a audit for a client, and the contractor had just started placing a compacted clay liner. In the past week or so, they had an extremely high failure rate. CQA technician out there was performing confirmation testing using a dry cylinder, quick moistures and oven dry moistures to compare. They were also obtaining samples, 1 points, and classifications, checking back to the original sample, make sure they were using the right proctor. And the contractor themselves, they were at risk getting kicked off the job, and they brought in a separate testing firm to compare nuclear test results in the same test penetrations as the CQA. And the guy did it. I watched him do it, and similar results to that the CQA got. So again, the same 4 questions. Number 4, why didn't the owner stop it? And just noteworthy is that the owner had multiple representatives on this site that were actually observing the construction periodically. They were on site going to different construction areas, but they were there and present for that. And so what was the cause of this one? The test preparation didn't meet the requirements of ASTM D6938, which governs your shallow nuclear density testing. The test was cut by the compactor. It was pretty rough. You could visually see that the surface wasn't smooth. You could visually see that there were big voids below the gauge, which greatly alter the results. And, a CQA technician obviously didn't have experience because they didn't catch that. And why didn't the engineers stop it? That's another interesting one because they were on site. They were also performing CQA. They were doing training and oversight of their technicians. The engineer knew there was an issue, but they didn't know what the issue was. They couldn't figure it out. Um, why didn't the earthwork contractor stop it? You know, they knew there was an issue. They brought in the separate testing firm, so they did identify the issue. The testing firm that they brought in was a reputable firm known for CQA and earthwork throughout the region. But their field technician also failed to identify that the test preparation was an issue. Thereby, they didn't do any, good service to their client, to the owner. They just went along with it, and that was two wrongs, and two wrongs don't make a right. Why didn't the owner stop it? Um, yeah, that one's an interesting question in and of itself. And talking to the owners, when I started listening or mentioning my concerns, at least one of them agreed with me, and they thought they had seen it too, but they didn't want to speak up. They were primarily worried, that they would be directing the contractor at that time, and you direct the contractor. Everybody's worried you're going to get a change order. You make them stop. They're worried, you're going to get build time for lost operating and such standby time. So that was a big one. Lack of training. One of the guys seemed more knowledgeable than the other. So I always recommend everybody that's out there, should understand what's going on the job site and be able to identify at least major things like this. So we'll move into standardization and calibration of your nuclear gauges and why we use the nuclear gauge to begin with. Whoops, must have hit a wrong button. There we go. All right. So why do we use a nuclear gauge? It measures the density and moisture of compacted materials like soil and asphalt. And it's a quick determination method. That's, another primary reason we use it. The sand cone, drive cylinder, a lot slower. You end up with bigger penetrations. You have to deal with filling the penetrations. You have to deal with sand in the area, getting the sand out. So the nuclear gauge is convenient with all the other methods that do density. You still need to get a moisture reading. So now you've got to take a separate apparatus, separate time to get your reading. So the goal is ultimately to get a quick and highly accurate moisture and density reading, which a nuclear gauge will give you on the proper soils. It's important just for those of you that may not know how it works. I just wanted to throw this in. Radioactive sources, you have gamma rays for density, neutrons for moisture. They're emitted from the source and from the gauge, and then they have sensors that detect how many of those particles come back. For density, it's going to be your gamma rays. More particles detected equals a less dense material. Moisture, the neutrons are slowed down by hydrogen. So if you get a lower count, it's a higher moisture content. But that's all the gauge is actually doing. It's emitting the radiation, and it's recording the amount of radiation coming back to the sensors. That's all that the gauge itself does. It's all the electronics that do the other thing. These are just your counts, and the counts is what determines your test. And it's important to understand the counts. The counts get into your gauge calibration. The gauge should be, usually every manufacturer requires annual calibration. And what the calibration does is it establishes a ratio of density and moisture counts for the gauge that correlate back to known densities. And they correlate back with a specific standardization block that has a known and stable density and moisture content. So you'll see those white blocks with the gauges. Those are your standardization block. And I'll have a photo here in a couple slides just to show you for those of you who may not have seen them. And it'll give you a chart. Your calibration gives you a chart with these different ratios that pertain to different densities for both your wet density and moisture. And then you derive your test results from these ratios. And these are the formulas here. There's a density ratio, the test density count is going to be divided by the daily density standard count. And the same for the moisture ratio. Test moisture counts divided by the daily moisture standard count. So that's why the standard counts are somewhat important. This is, excuse me, an example of a chart you might get back with your calibration. Just different density ratios, and they correspond to the different wet densities here. And so why is a standardization necessary? You know, a lot of people don't realize how important it is, but it's meant to overcome both decay and environmental factors. Your radioactive sources decay over time, and they only have a certain serviceable life typically. And the older they are, sometimes it seems like the more maybe they decay or rapid. Never been able to really prove that. I don't know if that's true, but some gauges that I worked with that were really old seem to have more issues. Then temperature, things like that can affect the operation of the gauge as well. So really the result is if you're trying to compare apples to apples, a raw count of 50,000 today doesn't mean it's the same thing yesterday, 3 months ago, 6 months ago, or 3 months from now or tomorrow. And that's what the standardization is trying to equalize everything and make it so that you can compare apples to apples on a daily basis with your results. What is the standardization? Typically a 4-minute test, and it's performed on the standardization block for the gauge, typically at the start of each day. Again, it establishes your daily baseline. I'll get into showing you that here with a sample calculation. And, you know, it's the most important part is making sure that your gauge has the right standard in for the day. You get the standard wrong, and I've seen people do it. I've done it myself, and it'll mess up your day. You'll get all kinds of funky results. Excuse me. Um, so the gauge, this is standardization, a couple pictures. You can see a serial number on this white block. That's a 3-inch block. That's for the CPN. That serial number is assigned to that particular gauge. You shouldn't be swapping the blocks around. I've seen people swap them. They have issues. They don't know why. Um, there's other things, you know, you get basically has to be a smooth contact. You want intimate contact between the gauge and the block. And there's certain ways you put certain gauges on the block. The CPNs that we use have a little button-like thing on the block that you slide over an indent so they match up, and you got to have it square on there. You can't have it sticking half on, half off, things like that. Um, so yeah, um, you can get your results messed up even if you're trying to put it on the gauge. As an example, here's some manufacturer's procedures I threw in for the porta probe and the Troxler 3430, both pieces of equipment I've used in my career, so I was familiar with them. But procedure, you put the CPN, standard block, 3 inches, take the standard count on a dense material, compacted soil, asphalt, or concrete. If you have a thin block, a 2-inch block, which I've never used, you take it on the shipping case. I've seen people do it, but I've never done that. Troxler, get my phone off here. Sorry about that. I thought I had my phone silenced. Place the block on another, again, a flat surface, 10 feet from any vertical surface, 33 feet from any other radioactive source. And again, it should be on an asphalt concrete, at least 4 inches thick, and a density of 100 pounds per cubic foot. And then the last part, the right side of the gauge, farthest from the handle, should be against the metal butt plate. So the Troxlers have that butt plate, and you got to make sure that that edge of the gauge is against that. And you'll see people that don't do that, and they get faulty results. And that messes up your whole day, like I said. And checking the results is critical. A lot of people don't bother to do this. You know, it's in the manuals. You need to do it. We keep log books of the standard counts, but you need to keep record of all the standards and make sure that they're falling within the tolerances for the gauge. If you don't, you have an issue. The porta probe, they give you an XI ratio that it needs to be between 0.75 and 1.25. Of the previous counts, and it'll give that on the screen, so that's nice. You don't have to calculate anything out. Troxler 3430. I remember you had to take the average of the last 4 days of operation of the standard counts. get an average of them, then compare them to your current standard count for both moisture and density, figure out if they're within 1% on moisture or density and 2% on moisture. And if they're out of tolerance, you need to stop. You need to figure out why. Sometimes, like I said, there's dirt. Could be the surface you have it on. If you're doing it out on the clay, maybe there's a stone under there. You got voids under the standard block. So just to get into some of the math behind the modern gauge, I was really kind of comparing then to now, but it's really the same thing, only now the computer does it for you. You took your standard count in the morning, you get and record those values both for moisture and density, you obtain your raw counts from your test, and then you had to divide it out, get that ratio I showed you. Then you had to go to the chart. Most of the time I was unlucky. The values never matched what was on the chart, so you had to interpolate, figure out your interpolation. Then you got to convert it through your other formulas to get your result. And that's just shown here in this slide. Density ratio, your density count divided by your standard count. And like I said, modern gauges, they all do it now for you. And so how do you calculate it out? Why is it important? Well, it just shows you how the basis of your gauge is set up. And I think it's good for you to know. So you have your calibration chart, and your daily standard count is, say your daily standard count for wet density is 550,000. Then you're out, you take your first test, you get a raw count of 48,000. You're going to need to calculate out your ratio. So you take your 48,000, divide it by your standard count for density. That gives you a ratio of 0.087. So that's not on the chart. So you got to figure out how far off between these are. If you subtract the two, it turns out, 0.7, it's going to be 70% of the way from 0.8 or 0.08 to 0.09. So you can use that 70% with your 95 pounds per cubic foot wet density and plug it into the equation, use your 95, get your difference between the two first, your 110 minus 95, multiply those and add it to the 95 and you get 105.5. So now you got your wet density value. Now you got to go through the same process with your moisture counts, figure out your moisture density. Then you need to plug those into the equation. So you have your wet density and it equals the dry density plus your moisture density. And you want to solve for your dry density, which is equal to your wet density minus your moisture density, because those are the two that you have from the gauge. So you've got to manually calculate out then your percent moisture is your moisture density divided by your dry density times 100. And your compaction is going to be your dry density divided by your maximum dry density from your Proctor curve, and multiply that by 100. So now you have your results, and you got to figure out if it passes or fails. If it fails, the contractor's ready to kill you, and by the end of the day, you're ready to kill them because you got to keep taking tests, and it takes you forever to calculate out. So it's a lot simpler with these gauges that calculate it out quickly. So some of the key takeaways, though, for this is really, I was trying to show you that, the annual calibration is critical, and that establishes your density relationships every year. They're going to probably change a little bit due to the decay. Then your standardization is going to account for that decay throughout the year. It's going to set up your test for the rest of the day for that day. And it's really important and critical as far as the accuracy is concerned. And then an action item, always perform the standardization at the start of the day. A lot of people don't do that. And you see some results are erroneous because they haven't, and people scratching their heads. That's one of the biggest takeaways, the calibration and the standardization, doing it in accordance with the manufacturer's recommendations. Then we get into what are the other variables? I talked about that. I believe the calibration and standardization are big, but There's a lot of other things that can go wrong. Some are specific to the gauges themselves. And I talked about it a little bit, test preparation. There's different methods that people will have the um, test area cut, different compactors here with blades. This one was cut by a dozer. I've used foxhole shovels before, flat bladed shovels. The best thing that seems to produce the best results to me is a dozer. Their blades were made for cutting and grading. Compactor blades weren't. And a lot of times, compactor blades will tear. That's what they were using on that one project that I told you about, the 2022 project. They were cutting it with a compactor, and one of my suggestions was they cut it with a dozer, and they started getting better test results when they did that and got rid of the voids below the gauge. Surprisingly, huh? Um, so the test preparation, again, there's ASTM D6938, requires a smooth, flat surface, maximum contact with a gauge, a perpendicular hole when you're doing the direct transmission to the proper depth, which your proper depth typically is not going to be the depth of the test. It's usually going to be a couple inches below that. You just need to look at the manufacturers, but some of the pins already account for that. Like the pins we use with a CPN, 8 inches is really a 10-inch driven 10 inches deep. Um, Representative material, of course, the results, if they seem skewed, you should investigate. I've found rocks, I've found frozen materials, things like that below stuff because the results just were so crazy. I knew there was something wrong, but people that don't have much experience and rely on it sometimes don't get to the proper conclusion. You should always investigate if you have an issue and try and get to the bottom of it. And then again, follow the manufacturer's recommendations. And as I mentioned, there should be no voids between the probe and the soil. I always tap the gauge rearward with my foot to ensure that you have good contact. That's the first thing I do after I get the probe down. Another recommendation that we like to make, to minimize your exposure to the radiation, you see a lot of people have the gauge in the air and they're putting the probe out and they're getting more exposed to radiation than they need to be. One of the cheats that we use is to make an outline of the plate, and then you can really get the gauge in the hole without even having to have it in the air. So it minimizes the amount of radiation you're exposed to. Some of the cheats, I call them cheats, are things that can impact the overall quality of the test, give you faulty results that you shouldn't be getting. Um, and I think, these three here are some of the biggest ones I see. Tamping, sometimes technicians have tampers to help level off an area, but you'll see technicians go crazy with a tamper and you either increase the compaction, increase the moisture, or both. Vibratory compaction, if it's not a part of the compaction protocols, it should be avoided. I've seen where contractors drive a vibratory machine up there and they want you to test on top of where they had the smooth drum and they vibrate it to get the moisture up, and that's not what you should be doing. Running heavy equipment, same thing. So those are things that should be avoided. Other nuclear gauge variables, manufacturers, you do see a difference in results between different manufacturers. I see CPN gauges, at least on the soils that I use in Ohio, I think I've always seen tend to be closer to the actual moisture. Trucks are slightly different. And it's not a major difference. I'm only talking a percent or two here. But sometimes it's enough to make a difference, and you need an offset with one gauge and you don't need it with another manufacturer. Um, and as long as you know your offsets, you can make any of them work with a proper material. But then that leads you to some materials are not suitable, such as gypsum or anything containing hydrogen, because the moisture is going to be impacted. Offsets I briefly mentioned above there. The gauges have different offsets: moisture, density, trench offsets. And if any of those values are in the gauge, they'll throw off your test if you're, unaware that they're there. If they're not supposed to be there, you'll be getting faulty results. So those should always be checked. As a technician, you should make sure that those variables aren't in there. And if they are in there, you should make sure they're correct, and you should have them documented on your testing forms. Um, Test duration, that makes an impact too. You have 15, 30-second test, 1 minute, 4 minutes. Usually the standard on job sites is 1 minute, and they're fairly accurate. Sometimes a 4 minute will, give you just a slightly more accurate result. But the quicker they are, the less accurate they are. It's been my experience anyway. The depth of the probe, direct versus backscatter, is obviously going to impact your results. Wrong proctor, wrong information input into the gauges, and other equipment in the area I've had where their vibratory smooth drum is, getting done for the day and they're running by, and for some reason that impacts the gauge. And, it's not where I'm testing, but it's close by. But I've seen where it does it, and you get them to stop and you get different results. Excuse me. So now I'm going to get into the other variables that really influence all the compaction test methods that you do. And I'll just go over a brief list of them here. Your material sampling, how you sample it, soils laboratories, subgrade preparation, your material type, material placement, methods, thickness, material moisture conditioning, the uniformity of the material compaction, not just the equipment, but the procedures, your test location preparation we talked about for the gauges, your test procedure is important, and then interpretation. You think it's pretty easy, but again, it's not. So we'll start with material sampling here. This is kind of a sample borrow area I grabbed from one of our projects. You can see different test pits here. They all represented a certain volume of soil, 809, 810, 811 here. I'm going to refer back to these in a moment just as an example. But, the sampling strategy really should be based, I think, on your proposed excavation method. You have excavation primarily with your scrapers or pans, and you have excavation with an excavator and haul trucks. Your scraper is only going to take off 2, 4, 6, 8 inches of soil at a time, whereas your haul trucks and an excavator are going to take feet off at a time. And you can see here in this photo that there's different types of soil being mixed here. You got a brown clay or brown sandy or silty something on the top, and what looks like a gray clay down here at the bottom of the cut. And those are all getting mixed together, which, for some things may be fine. For other things, it might not be fine. So it depends on the use of it. But when you're trying to use proctors for the different materials, there can be a huge difference, and they may not be compatible. This is a test pit example, a sampling where the engineer, suggested we had a sample from 1 to 6 feet, 6 to 11 feet, and 11 to 16 feet. So one test pit, 3 different zones. And if you look at back to this 809, 810, 811, I put together a profile here. It's not to scale, but we started with a topsoil, modeled brown silted clay, brown clay, gray silty clay, gray silty clay with increasing sand and gravel content. And you can see how this sample A zone from 1 to 6 feet covers multiple soils, and that could be detrimental to the project, especially, if your values are significantly apart. And as an example here, sometimes the materials are just too far apart to make a composite sample work. In this chart I put together, sample 1, proctor was determined to be 131 is your maximum dry density and 12% optimum moisture. Soil 2, 121.8 and 14.8 was the optimum moisture. And the project requirements are 92% compaction and optimum moisture to +3. So if you're combining those, you're already going to be, probably having to meet a moisture of 14.8 to 15. So your window of moisture has greatly shrunk. And if you're trying to compact this soil number 2 to meet the same requirements, you're really going to be at just about 98.9% of the 131 value. So you got a really small window where this material is going to work together, if it'll even work together. And that's something just to keep in mind that really impacts results, and it impacts the quality of the job. Another thing to remember is that soils are a lot like a needle in a haystack. You know, the soil wasn't deposited, created, whatever you want to say there, uniformly. It goes up and down. I've been on projects where the soil varies by the foot, it seems, you know, going horizontally or vertically. And it goes from a silty clay to a sandy clay or a silty sand in a couple feet. And those sites are really hard to work with. And you got to take that into account in your planning. And a lot of times, unfortunately, that doesn't happen. People should look at the geological logs, the boring logs that are on site and see what's there and adjust their sample plan accordingly and adjust it according to what you encounter as well. Sometimes all the soils that you think are good aren't going to be good. There's going to be something there you didn't expect because it's between the borings. So some of the pre-qualification sampling tips, you know, basing on an excavation plan, I think what type of equipment that can really help. Technician, again, should be familiar with soils, and they should be the one performing the sampling, ideally the same one that'll be on site later, but at least somebody that's familiar with soils. Um, Technician and contractor, if they see something that looks suspect, that's not going to work, they should speak up while they're sampling. A lot of times that don't happen. You see contractors dig in the pit, they dig some kind of junk out of there, and they never say anything about it. And the technician doesn't either. And I end up having to resample and do other things. Maintaining good logs, whether it's your test pit logs, sampling logs, details, free water, things like that. Accurate and complete chain of custodies. Chain of custodies really should be treated with care. In this industry, it seems like a lot of times they're not treated that way, but they should be treated, you know, with the same care you treat groundwater samples with, blood samples, whatever it may be. And then again, safety first, especially dealing around test pits anywhere in this. Safety should always be your first consideration. I should have put that as a first bullet point, but I wanted to hit on some of these other ones first. Excuse me. Soils laboratory, and they're not all created equal. And I was on a job site. I took like 75 samples or something, and they submitted the first 20, 25 samples. While I was taking more samples, and the junior engineer calls me up and she's like, you know, where'd you get the sand from? Why are you getting sand? You're supposed to be sampling the clay. And she's yelling at me about it. And I'm like, I don't know where you got sand from, but I turned in clay. I said I turned in silty clay, I turned in sandy clay. There was some stuff that was borderline silt, but there was nothing that was sand. And you know, that was the first 20 samples all came back as sand, and that doesn't do good to give you much confidence in the soils lab at that time. But primary purpose of the soils laboratory is pre-qualification of materials and then confirmation of the materials afterward. Pre-qualified materials by classification. Typically, once they're approved, you'll have run a Proctor curve and then sometimes hydraulic conductivity for compacted clay liners. I'm just giving you these. I'm going to breeze through the next couple slides here. They're really meant just kind of as background, but I put in some compacted clay liner. Soil requirements, typically low permeability soil is what you're trying to achieve. Different classifications of soil. Michigan has some different ones than Indiana. Most of them, you know, like Indiana has, they're going to need to contain a minimum 50%, passing the number 200 sieve. Clay content greater than 25%, and soil plasticity index of 10% or greater. And I'm not going to get into all those tests. Just to mention a soil classification, you have your triangle with your three main constituents of the soil: clay, silt, and sand. Different percentages result in different materials. The laboratory determines, you know, I'll go over a couple laboratory sheets just as an example here, but you end up having your classification symbol, whether it's a CL is a lean clay, and it's really a clay with a low liquid limit, and you have your CH is a high liquid limit clay. Those two would be something that would be approved for most of the compacted clay liners. Looking at the laboratory data sheet, You can just see, I just included this just to show you the different sieves they go through. And then to get your fines below the number 200 sieve, they use a hydrometer and give you the values, and they figure out the different percents. And that's what somebody needs to look at to determine if the material meets the requirement for the project or not. And unfortunately, we're doing our audits of projects, even projects we've worked on. We see where soils don't meet it. There will be something that's out of spec there, and somehow it was passed. Sometimes it's even been approved by a regulator, and there's no reasoning for it. And you can't use it. You find it gives you problems if it gets by. Again, I mentioned I just threw this in here as a moisture density curve, just as an example, in case some of you aren't familiar. They pound the different points, and computer program figures out what the maximum dry density is, and your optimum moisture content for compaction of that material. And I threw this slide in here. I already really discussed it, but baffled. I was baffled when I got 25 results back that say they're sand, and I know they were clay. You don't want to be baffled with your laboratory. You want to have confidence. And so there's some tips. I think check references of laboratories, especially laboratories that might be for, within a firm that aren't really a national firm, but they do their own testing and you want to send it there. Check references. Accredited laboratories, I think, are often a bonus, but just to remember, errors can happen even with the best. I've seen it. Errors happen even with the best. You always got to be diligent, review your results, and then extra set of eyes on the results during review, I really think helps. That used to be a practice I'd see when I was first in the industry. But before I left, I didn't see engineers getting their work reviewed by anybody like we used to. You'd see nobody's initials on the work anymore. Engineering, again, I touched on one of the main things is a review, but materials failing to meet project requirements. Do you retest? If they do fail to meet requirements, there needs to be proper communication. They need to be delineated. What are you going to do with them? Soils, obviously. If it's coming, out of the ground, even from a stockpile, it's not as easy as geosynthetics are, where you can just make a separate stack of a couple rolls. It's going to be a major endeavor to move and relocate soils, and it's going to be costly. So making sure you have those boundaries, a technician out there, making sure that if the material is rejected, it's not being used. Engineers making the curves and the best fit line optimum curves. This is the data behind a curve here, and it's all the points. So if you're plotting it on the curve and you can't tell, you can look at your chart and see if it passes or fails. But we've had problems with the BFL curves before. Engineers need to make sure that they work for the material. Sometimes you need different curves. You need different curve for brown clay, different curve for the gray clay. So there's a lot to it. It's a lot more than meets the eye, even with a best fit line of optimum curve. And sometimes you get those soils that just won't make it. So now I'm going to spend the rest of the time here predominantly in the field construction and then our test results. Field construction, everything starts with a subgrade preparation, that foundation that you're putting your compacted material on. That needs to be a firm foundation, and it needs to stay firm throughout the use. So you want to remove anything like soft areas, things that are, gravel seams, things like that, that might leach water and pump water up into the foundation and weaken it over time. So proof rolling is typically done, and proof rolling should always be done in accordance with the project requirements. You'll see projects where, we're out there auditing and they're running over it with an empty truck, or they've got a smaller vehicle than what is specified. And it's that way for a reason, so they can test the strength of that foundation and ensure that it's going to hold up. Because these issues, if they're not remediated now, they will come up later. Trust me, I've seen people take shortcuts and you're on lift 4 of a compacted fill and everything's starting to pump because you didn't get all the sand seam out or you didn't get all the water out of the sand seam. So things like that happen. Material monitoring, whether it's, borrow area itself or pre-processing, it should always be monitored. Make sure that the material is always in conformance. Excuse me. Lift placement. Um, some things that are critical to lift placement, making sure your lift thickness is within tolerance, your moisture conditioning, and that the material is homogeneous. Things that are going to impact compactive energy, like big clods, rocks, things like that, deleterious materials, they need to be removed so that you get the adequate compaction throughout the lift. It's not just one area where you're taking a test. Lift thickness issues that we see, um, you know, a lot of times operators are putting in for an 8-inch loose lift on a compacted clay liner, they're putting in 0.8 or 8 inches, and that's 10 inches. And, whether it's intentional or, they're playing dumb or what they're doing there, sometimes they may not know, but CQA should always be verifying. The thickness is really important because you're usually trying to knead the lifts together, and any of those clods or things like that are going to impact that ability as well. Lift thickness, some other issues to think about. Fat clay with squeeze out here. What is considered the original lift? Where does the next lift measurement start? Those things all need to be worked out ahead of time with a contractor. They should be in the test report, test pad report, or something like that too, because you start getting a bunch of these lists where you have this excess material on it, and all of a sudden you're too thick, um, and you're not getting your proper compactive energy. Moisture conditioning, that's another big one when you have to add water for whatever reason. You need to make sure that it's properly incorporated. It should be disc and worked into the entire lift, not just the area that's going to be tested. And sometimes you'll see that, the contractor will run over the area you've been testing, but he won't work the rest of it. At that point, I just reject the rest of the lift until they do something. Lift interfaces are important so that your material bonds together, particularly on slopes and then low permeability soils where you want them bound together. But it's important to get a good bond between the lifts. And one thing that I see is often a problem is people don't monitor your boundaries of the lift control. Like if you have this is a roadway or a cell or something you're tying into in the future and you're running, one side of it, they put down lift one and then they put down lift two and you get slough from putting it down. It's going to fall over that portion. Then lift three is going to fall over more and so on and so on. And you end up not getting adequate compaction outside this area because you got material falling over and then they tie in and they don't go tie in back far enough. I've seen this on, landfill cells that I worked on where I surveyed the points, 10, 15, 20 feet sometimes by the time you get up to 6, 7, 8 lifts. And the contractor doesn't want to remove it, but they need to. And you can see once they start cutting into it that it wasn't properly compacted. Compaction, I showed a different type of compaction. This is a toe behind here. I tried to get a photo of all the different types, other than a smooth drum. And at least the main heavy equipment, not the walk behinds and such. But all the equipment needs to be correct. It needs to have the correct attachments, such as blades on your 815, 825. They're all designed to operate with those blades on, and those blades have a lot of weight and balance the machine out. Same thing with those drums. If they need to have ballast, some type of fluid, sand put in them, they need to be in there. Number of passes often is neglected. Perpendicular compaction can help. Sometimes, we get engineers that say, man, the material, if it passes, meets your compaction criteria with 4 passes, you don't have to do 6. But, I don't know how that really is, especially on low permeability materials. Sometimes you don't get your required hydraulic conductivity doing that. Wheel spins and abrupt stops should be avoided. Consistent speed should be used, and overlap. These are all things that come into, are the results good or not? And a lot of times people aren't documenting those. So then you get your material placed, it's compacted. So now you're taking your test. I've already talked a lot about the test preparation. You want a smooth surface. It should be meet the requirements of the ASTM. Excuse me. This is moisture density testing, just a photo here. It looks like probably could have cut down a little bit to get below the pad's foot mark there. But that may be because they cut it with it, I'm not sure, but um, it just shows, the variability in an area too. You can have an area that you can test, an area that you can't test, and I like to have the whole area that looks uniform so you know that you're getting a valid test in the area. One of the biggest takeaways I want to leave you with, though, is this one here, your field result interpretation. Your results should always verify what you're visually seeing. If you have a compactor rising up out of the soil like this one in the left photo, and your test results are failing, there could be an issue. If you have the proper moisture and the test is failing, there's probably an issue. Um, Likewise, a photo on the right, if that one is passing, you probably have an issue because the compactor's as deep as the cleats are. So you don't want that. Um, and there are things people can do to help with a field interpretation. Are they right? You can try and ribbon the material. Does the moisture seem right? Does the material seem right? Is it consistent? Color, things like that. 1-point proctors, they're often not specified, but that's a good way of checking the material. And what you want to do there, AASHTO T272 has 3 ways. You basically plot your test to see if it falls on a curve. And it has to fall within this blue window here. Your density has to be within two pounds per cubic foot, either above or below, which are the upper and lower blue lines. And your moisture has to be 80% to 100%, which is the left line and the right line. If the test plot's in there, it passes. It confirms that you're using the right proctor more than likely, as long as your material is the same. But we see a lot that don't confirm it, and people are actually saying they are confirmed and don't understand that they're not confirmed. So data review tips, for anybody reviewing it, I think you got to look for the calibration. You got to look at the daily standard counts, make sure they're acceptable limits. Confirm the borrow source matches. Is there any correlation needed? If technicians switching proctors all the time, most of the time that means that they're just trying to make the test fit. Examine your photos. Today you get photos right away pretty quick. It's easy to examine and then address concerns immediately. Methods for verification, I'm just briefly going to touch on these. Sand cone is a density where you have a sand of a known density. It fills a hole, gives you your volume of the hole, and you weigh the soil you excavated out. You can do the conversion for density, but you need to do a separate moisture. Same thing with a drive cylinder. You have a cylinder, you pound it. It's a known volume. You get your density there, but you still need to do your moisture calculation separately. So there's multiple ways you can do your moisture. There's quick methods, microwave, speedy moisture, hot plate probes. O-House has some devices that are used. This is a speedy moisture here. It used, I can't remember the powder offhand, but it formed acetylene gas, which was the pressure that correlated to a moisture. But any quick method you use needs to be compared back against the dry oven method. And the dry oven method really is the gold standard. It's going to be the most accurate, but it's an overnight test, and the results aren't quick. So it's really your confirmation when everything else fails. These correlation tips, correlation verification tips need to be prompt, need to have prompt review, need to correlate them back to the original proctor. We see that doesn't get done sometimes. They need to be correlated back to the original nuclear test. Does it pass? Does it fail with a proctor? Is a nuclear test accurate? Is there a correction needed? If a correction is needed, you need to address it immediately and get a correction in there and document it. So in summary, really in closing here, there are many factors that determine the accuracy of a nuclear gauge test and whether it's valid. There are instances where the gauge is going to be incorrect if you didn't get it calibrated, if the standardization wasn't done properly. Those are the 2 major ones. It's not as simple as plug and play. Calibration needs to be done. And second big takeaway is that the test results should confirm what the CQA tech, the QC tech is seeing. There could be other issues as well. So you always got to look at the data as a whole. Like if the test plot's above the zero air voids curve, typically they shouldn't do that. And, avoid sole reliance on the gauge, especially without confirmation testing. And then confirmation verification testing should be routinely performed. I like having tests performed when we get to a job site. A lot of specifications don't require it. And I know I'm right here at the hour. I'll take another minute or two here and I'll answer questions. I'll just finish up on this slide. A lot of reason is many CQA technicians don't know how to perform a sand cone and or a drive cylinder for that matter. And to have any value, again, these results need to be correlated back to the original proctor and to the gauge. So I want to thank you for joining me. My next webinar is September 18th, Thursday. I'm going to look at extrusion weld evaluation, what to look for before, during, and after welding to identify if there's an issue, help you get peace of mind that you have good quality on your job, and give you hopefully some tools that you can use to hold the installers and other personnel accountable and get good welds. So with that, move on to the questions and answers. Let me check here to see if there are any questions. Ooh, did I do it? Am I still on there? There are no questions. I do not see any questions. All right. So, yeah, I don't have any questions. I do appreciate you all tuning in. I hope you took home a few points here that'll help you on your compacted soil projects, and especially with your nuclear gauges. They're a great tool. People just have to use them properly. So thank you very much. I look forward to seeing you in September.